we're going to talk about fluids, by which we mean liquids and gases, and we're going to start with liquids. Now, a fluid can conform to the shape of its container, but a liquid takes the shape of the container without changing its volume. And that proves, by that definition, that cats are liquid. Hey, the cat's fine. The cat's going to be fine. Okay. So let's talk about liquids. Have any of you scuba dived? Yeah, okay. Now scuba diving is way fun. I went to high school in Guam, and that's what we did after school. Our physics teacher had only had one class of physics in his whole life. And he taught us what he could. He taught us a little bit of physics, and when he ran out, he showed us the most wonderful pictures of sharks. And that's what I learned in high school physics. And he was also the faculty advisor for the scuba club. And so we would go after school and go scuba diving and snorkeling. Now, if your ears get clogged or you have a hard time with your sinuses and you go down snorkeling or scuba diving, what happens? Yeah, it feels like your head's going to explode. It feels like, you know, you're being crushed. Okay, and that's this pressure of the fluid around you. Now, earlier in the class, we defined pressure as the force applied divided by the area over which it's applied. And with a liquid, we just need to modify that definition slightly and say that this is the component of the force that is perpendicular to the surface that we're finding the pressure on. Now let me see if I can give you a visual for that. Many years ago, when my children were young, my father decided to take all of his posterity to Disneyland on a very hot August day. He didn't decide to pay for it, he just decided to bring us all. I paid a fortune to get my family into Disneyland. And it turns out that when we got there, we found that every other American family was there with us, and a lot of families that were from other countries. And during the course of that one very long, very hot day that I paid a fortune for, my family got on two rides, and one of them was Dumbo. And the other one was 20,000 Leagues Under the Sea. Does anyone remember that ride? It doesn't exist anymore. They got rid of it finally. It's replaced with Nemo. But at the time, they had this great, big, huge swimming pool and a submarine. And you waited in line for 5 hours to get on this submarine, and the submarine took you on this journey. And it dove down 20,000 leagues under the sea, except for 5 hours you were watching it just go around on top. And everyone had a little porthole that they could look out of. And if you look out that porthole, you saw these wonderful, beautiful fish that were plastic, and they were held to the bottom of the swimming pool with fishing line. I don't know what Walt was thinking, but this was not a Disney ride. Anyway, if you think of that circular window, there's two pressures on it. You got the water pushing in, and if you take the total push in and divide by the area, pi r squared, you have the water pressure. And then you got the air pushing out. Now, clearly they had to pressurize the submarine because we were going so deep. But the air pushing out, you divide that by pi r squared, and you get the pressure, the air pressure, going the other way. Okay? Now, what should matter? We already said that the deeper you go down in water, the bigger this pressure becomes, and it starts to make your head feel like it's being crushed. What else should matter besides how deep you go? Brave soul, raise your hand. Come on.
How much is pushing on you?
How much
is pushing on you?
Yeah, how much water is above you. Okay, and that has to do with how deep you go. Well, you mean the surface area of the body of water? Like whether it's a lake or whether it's a pond?
No.
Okay. What else? What else should matter? How fast you go down is going to determine how bad your headache is and how quickly your head explodes. But fortunately, that's not going to affect how big the pressure gets. No matter how fast you go down to 100 feet, it's still going to be pushing on everyone the same down there.
How big you are?
How big you are, okay, that will have to do with the total push, but not the pressure.
How much area it's pressing on?
That's how big I am. The density. Whether you're going down in a pool of fresh water, or whether you're going down in a pool of salt water, or whether you're going down, heaven forbid, in a pool of liquid mercury, okay? It matters. Now, so the only two things that we find matter are how deep you go and the density. Now, how deep you go can easily be demonstrated with this cylinder. It has some holes drilled in the side, and you can see that the deeper in the water, the greater the pressure with which it's streaming out of the hole. And that demo's just disconcerting. That's just going to distract us and make us uncomfortable until I get rid of that. Let's just stop that. Okay. Now, my good friend Jeff Adams, when he was a teenager, and he was a geek, he was bound to be a physicist, his family bought a summer cottage on a lake in Canada because they're Canadian. And he got to that lake and decided, I want to explore that. And so he decided he was going to explore the entire bottom of that lake. And the way he was going to do it, he felt, was ingenious. He didn't have any scuba gear, but he did have a scuba mask. And he found a way to weight his feet down. So he put on that mask, and he weighted his feet down, and he was going to walk across that lake on the bottom. And first, he went and got the garden hose, and he hooked the garden hose to a big piece of styrofoam. And he was just going to breathe through that hose as he walked across the bottom of the lake. And he was really surprised that Jacques Cousteau had not come up with this before. It just seemed so obvious. Now, it turned out badly. Anyone know why?
His lungs don't have the strength to push air all the way out.
Exactly. The lungs do not have the strength to push air or to bring air all the way down. If I look at the pressure at the two ends of that hose, there's much more pressure on the bottom of the hose than the top. Which way is the air going to flow through that hose? Up! This is a great method for getting all of the air out of the Jeff. And that's what it did. But that wasn't good. Okay, so that is not a good plan. Okay. Now, let's find a formula for the pressure in a fluid at a certain depth. Now, this is a little bit of a derivation. It's not going to hurt. It's not going to take long. It's going to be really quick. What we're going to do is we're going to go down to the local pond, Bozeman Pond, and we're going to carve out mentally with our mind a block of water, a chunk of water. And we're going to draw a free-body diagram for that chunk. Now, there's lots of forces on that chunk, sideways, but there's only three forces that act vertically. There's the weight force, the non-contact gravitational force, the mass of the chunk times g. And then there's a force pushing up from below, the water beneath this chunk, and there's a force from the water above pushing down. Now, in both of those cases, I can write them as the pressure at that point. That's how much force there is per unit of area, times how many units of area I have on that chunk, top and bottom. Now, if I balance all the forces, and why would they be balanced?
Not accelerating.
Because that chunk doesn't know he's special. He doesn't know he's different from the neighbor chunks. He's just sitting there with his brother water. Okay, he's not going up, he's not going down. So that free body diagram has to scream balance. So the one force up has to balance the two forces down. Now I'm just going to meddle here. I can write that mass as the density, that's the number of grams in 1 unit of volume, times the volume. How much mass there is per unit of volume times the units of volume. I can write that volume for this cube, this chunk, as the area of the top and bottom times the height. And now you see that every term has the area in it. I can divide both sides by area, and I get the grand high equation for pressure in a fluid. I'm going to write it over here. The pressure at any point 2 is equal to the pressure at any point 1 plus 3 things multiplied together, rho, g, h. Now, as long as I know the pressure in the fluid here, I can use that formula to find the pressure in the fluid there. And so what we find is that the pressure in a fluid really depends on 3 things. We said it only depended on 2, but we were making a very, very strong assumption. It depends on the density of the liquid, it depends on how deep you go, and the last one, it depends on what planet you live on. We assumed we were going to stay on Earth, and in that case it only depends on 2 things. But if you go to a different planet with a different gravitational field strength, you can go a different depth before your ears pop. Okay? Now, typically, in 99.99% of the cases, we choose P1 to be at the top of the lake. So what's the value of the pressure there at the top of the lake? Is it 0? It's 1. 1 what? Turns out it's 1, we call it an atmosphere. It turns out that when you're at the top of the lake, you are at the bottom of an ocean. A fluid is either a liquid or a gas. And when you're at the top of the lake, you are at the bottom of 30 kilometers of air. A vast ocean of air. Now in Bozeman, not really 30 kilometers because we're up so high, but still, it's a considerable amount. And so the pressure at the top of the lake is not 0, not even close. It turns out that it's 101,325 newtons for every meter squared. Now again, a newton is only 1/5 of a pound. It's not a very big force. And a meter squared is a big area. So this unit, although the official MKS unit, is pretty small. We call that combination Newton per meter square a Pascal, to honor a dead professor. Good thing to do. And typically, we work in kilopascals because a Pascal is so small. So we say that 1 atmosphere is about 101 kilopascal. And that's what they say in virtually every civilized nation on the earth, except one. America. Land of the free. We don't have to conform. What is 1 atmosphere in America? Anyone? 7. No, 7. That was really, really close. You were half right. Okay, it's not 7. It's 14.7 pounds per square inch. Pounds per square inch. What that means is that on every square inch of this milk carton, this great big sea of air is pushing with 14.7 pounds. Well, there's a lot of square inches on this thing. You'd expect it to just crumple right up. And it doesn't, because there's air on the inside as well, pushing out in order to balance the push in.